Good afternoon, everyone. My name is Ida. I'm a PhD candidate from Liverpool University. So today I want to share our current work about using AC impedance for crack monitoring in self-sensing asphalt. So the UK roads play important role in transportation system, and 95 of them are made of asphalt. However, they are facing more and more challenges. Increasing traffic, climate change, water damage make them more and more fragile, and the maintenance budget keep rising. To make roads safer, more sustainable, and cost-saving, digital roads have been proposed as a solution that enable real-time structured health monitoring of road infrastructure, facilitating informed maintenance decisions that enhance road safety, sustainability, and reducing maintenance costs. So to achieve digital roads, one of the challenges is how to capture the real-time health data of road infrastructure. So self-sensing asphalt material is a promising solution. So they are typically composed of traditional asphalt mixture and conductive additives, for example, steel fiber and graphite powder. So these conductive additives form a conductive network through the asphalt like a lever system. And when we apply a small current on it and the asphalt in a good condition, the current will flow smoothly through the asphalt. However, when a crack occurs, it will break some of the conductive network, so the resistance goes up, and we can measure that to inform the condition of the damage. However, there is a huge limitation is that even the specimens from the same batch, they have a different electric behavior. As we can see in the left figure, the green, red, black curve represent 3 replicant specimens. However, their electric behavior is totally different with each other during damage. That is because the asphalt material is a heterogeneous material. The small variation in the distribution of conductive additives will lead to a huge differences in conductive network, so making it difficult to establish a general relationship between damage and resistance change. So also making it hard to use for structural health monitoring. So the first thing, we need to improve the electrical stability. So we consider the electrical measurement. So there are 2 common used electrical measurements, DC and AC. The current study common used DC. It uses a constant current or voltage and depends on direct conductive responses. So that means the conductive additives, for example, steel fiber, they need to contact with each other closely. But in contrast, AC uses a continuous changing electric signal. Under certain excitation frequency, it can capture both conductive and compactive responses. So the compactive coupling generates displacement current. So that means even the conductive additives doesn't contact with each other, the electric signal can go through the small gaps between them. So compared with DC, AC measurement is less sensitive to the variation in conductive network and reflect the overall electric behavior of this material. So we choose AC measurement in our following study. And then we want to build a model to describe the relationship between the resistance and the crack length precisely. So as we can see in the first figure, AC current is applied on this specimen, and when a crack occurs, the equal potential line is destroyed, and the 2 probes alongside the specimen can capture this distortion and providing the information of the crack. However, when we apply it to a long specimen, things are going to change because the equal potential line becomes horizontal again when they far away from the crack. So we divided this specimen into 3 parts, and 2 parts which are far away from the crack is current uniform zones, which we consider it is not affected by the crack. And the other one is current perturbation zone. And these 3 zones are connected with each other as a series circuit. So first, we based on potential drop severity to derive a model for the short specimen, and then based on the series law to extend this model to a non-specimen. And finally, we get this equation. So as long as we know the initial resistance and the specimen's dimension, we can predict the resistance of the specimen at a given crack length. And then we want to verify this model against the real laboratory test. So we prepared 4 geometries of specimen, and for each geometry, we prepared 4 replicants. So it's 16 specimens in total. And we use a cutter to cut a load of 10, 20, 30, and 40 millimeters on the specimen as artificial crack. And the LCR bridge meter was used to measure the resistance of each specimen, and here are the results. So these figures shows how resistance changed during crack development. And as we can see, for each geometry, the 4 replicant specimen, for example, geometry A1, A2, A3, A4, they have the similar relationship between the crack length and the resistance. And more important is this repeatability maintained on the different measurement frequency. So that means the AC measurement can provide a more stable and repeatable result for crack monitoring in self-sensing asphalt. And then we want to verify the accuracy of this model. So the error was quantified by the deviation. It represents the absolute differences between the measured resistance and the model predicted resistance, as then normalized by a measured value. And based on the deviation, we generate the error maps. And here, geometry A as an example, the horizontal axis is the crack length, and the vertical axis is the frequency, and the color indicates the magnitude of the deviation. And follow this procedure, we generate 4 error maps for all geometries, geometry A to geometry D. And we find something in common. So first is deviation increase with the excitation frequency and the crack size. That is because at a high frequency, the capacitive coupling allows current to bypass the crack. So our model is overestimate the deviation. So overall, this model can capture the relationship between the resistance and the crack length, and at our recommended excitation frequency, the maximum prediction error is below 7% over all 16 specimens. And our work just just demonstrates the potential of using AC impedance for providing a stable and repeatable and quantitative result for crack monitoring in self-sensing asphalt. And that's all. Thank you.
Questions?